Hello students, welcome to Continuum Mechanics. Today we're going to do a lecture on the change of orthonormal bases, which is basically the idea of taking a problem, taking a vector or a tensor, and converting from one coordinate system into another. Now, in our previous chapters, in chapter 1 and 2, we introduced the concept of coordinate-free approach to vectors and tensors, right? The approach where we simply define them as, hey, this is a vector, hey, this is a tensor, and we don't actually prescribe a coordinate system to the vector or tensor, right? We can manipulate them in different ways. We can transpose a tensor, we can invert a tensor, without actually having to go into the nuts and bolts and see the coordinate system. In chapter 3, we introduced the components relative to a rectangular Cartesian coordinate system. And we introduced those components by describing the unit orthogonal base vectors which describe the coordinate system, describe the actual directions within our Cartesian coordinate system. And so those are the base vectors E1, E2, and E3, and where the magnitude of these vectors, the magnitude of each of them, is equal to 1. So they are basically unitless, right? They have no magnitude. They indicate direction. Now, even though we've done this, we introduced the concept of base vectors, we can still retain a version of a coordinate-free concept, a version of the coordinate-free approach when we are describing vectors and tensors. Let's see here. So we still get a version of the coordinate-free approach when we're describing vectors and tensors, in the sense that we can use any coordinate system, where we can describe the vectors and tensors using any coordinate system, any Cartesian coordinate system, right? So in this chapter, we're basically going to learn how to take a vector and tensor that is in one coordinate system, so one rectangular Cartesian coordinate system, and transfer it into another coordinate system. So let's kind of start with drawing two coordinate systems. Let's draw two rectangular Cartesian coordinate systems. Let's start with one we're all very familiar with. We all draw our normal little set of orthonormal vectors, where we have a base vector E1, a base vector E2, and a base vector E3. So that's one coordinate system. And we can say that's our original system here. So let's say E1, E2, and E3 is our original coordinate system. And let's say we introduce another coordinate system that's origin is at the same point. So we're saying that these coordinate systems have the same origin, but their orientation is not the same. The orientation of these orthonormal base vectors is not the same. Right? So then we can introduce this set of this new coordinate system that is rotated with respect to our original system. So E1, E2 prime, and E3 prime, where the prime is indicating that this is our new coordinate system. Well, if we can understand and define that there exists some relationship between these coordinate systems, then we can say that the base vectors of the two systems are related by the following equation. We can say that the base vectors of our new system are equal to some tensor dot product our original base vectors, where this tensor is called our transformation tensor. And it's important to note that we haven't defined the indices. We haven't defined the indices of this transformation tensor. And we'll see why we haven't. We'll work through the math and then find out what those indices are shortly. So, because both of the base vector systems, both our original system as well as our new system, since both of those systems are orthonormal, we can say that the tensor A is an orthogonal tensor. And the principle of having an orthogonal tensor is going to actually give us several identities, several very special identities that we're going to use and exploit as we solve the problems. So if we form a scalar product, let's fix this typo here. If we form a scalar product with our base vectors, we'll find the following. So let's do the scalar product, the dot product of our original base vectors dot our new base vectors. We'll remember that these base vectors, the magnitudes, are equal to 1. So when we do the magnitude of A and B here, it's 1 and 1. And we end up with a cosine of theta I j prime, where the j prime indicates that that j is associated with our new coordinate system, right? And we can, of course, rearrange this if we remember that our new base vector is equal to a transformation tensor dot our original system. If we remember that relationship, then we can plug that in here and find that our original base vector dot our transformation tensor dot our original base vector with indice j so simply remembering this relationship and plugging it in, right? Well, from this, seeing the indices that are given on our base vectors and the dot product that we're doing, these double dot products, we can say that the indices of this tensor is A I G. Excuse me, J. Now this cosine theta that we find, using the scalar dot product, this cosine theta is the angle that exists between the ith axes, or the ith base vector, and the j prime base vector. So this is actually telling us the angle of rotation from our original coordinate system to our new coordinate system, right? So with that knowledge, let's go ahead and state that our coordinate system, and let's copy our previous coordinate system here. Copy, and let's paste it here. Let's say that our that these thetas that we have let's actually define those in our diagram here. So we've got a cosine theta I, where I is our original coordinate system and J prime is our rotated coordinate system. There exists three numbers, so 1, 2, 3, right, for base vector 1, 2, and 3 with respect to our new and previous coordinate systems. So our I and our G go through those operations. Let's actually work through those operations ourselves. So let's start with our original coordinate system, and let's say, hey, what if we have 1, 1? Well, if we have our original coordinate system and we're referencing the angle between it and our new system, then here the angle between those is theta 1, 1 prime. And well, what about if we have our same original base vector with respect to the 2 prime? Theta 1, 2 prime. And then what about our original base vector with respect to theta 3 prime? Okay, theta 1, 3 prime. And we can continue this process and see that the transformation tensor is simply describing the cosine of the angles between the original coordinate system, right, our original base vectors, EI, and our new base vectors, EI prime, right? That transformation process. So from our previous arguments, we'll find that we can actually have a dyadic representation of this transformation tensor, where our transformation tensor is equal to EK prime and EK. All right, so our the dyad of those two. Now, another thing that we can find is because we have an orthogonal tensor, we know in previous work that the inverse of an orthogonal tensor is actually equal to the transpose. So from this, we can actually find the inverse relationship of what we started with. So we started with that we can find our new coordinate system, EJ prime, using our transformation tensor and our original base vectors, right? And we know that with orthogonal tensors, the inverse of the tensor is equal to the transpose of the tensor, right? Excuse me, my pen is acting up. There we go. So the inverse of the tensor is equal to the transpose. So if we rearrange our first equation here, we can actually find a relationship that takes us back to our original coordinate system if we're in a rotated position. And then let's introduce a new index here. So we'll say that our original coordinate system is equal to A transpose, so we're bringing it on the other side of the equation, times our new system, right? So it actually shows us how to reverse the process, how to go from our original coordinate system here to a new coordinate system, and how to go from our new coordinate system back to our original coordinate system. So let's go ahead and say original to new and new back to the original. Now, similarly to what we did previously, we can form a scalar product in the opposite order, in that reverse order, where here we have our a new system, dot product, our old system, and again we're introducing new indices here, n and m, and again the base vector's magnitude is equal to 1, so we can simply have cosine. Come on, pen. This pen is acting up today, or the laptop is lagging today. One of the two. There we go. So we simply end up with cosine theta of m n prime. And we can do the same process of taking what we know about em being equal to a em prime and place that into our equation. So substitute that in, and we get en prime dot a dot em prime. And of course, we've got to remember that this is transposed. So it's A transposed here. And we can say that the indices for this A then are A transposed NM or A MN. So switching the indices. And again, we want to indicate here that we are substituting in this equation to get everything in terms of our rotated or the new coordinate system, right? So these properties, this idea of being able to, or finding that the inverse of the tensor is equal to the transpose, enforces the idea that we have an orthogonal tensor, and from this we can further find this very interesting property of orthogonal tensors. We can note it in index notation, and we'll do that here. But the easiest notation to understand this is actually in coordinate-free notation, which we'll show next. So we have our A, I, K, A, J, K equal to A, K, I, A, K, J, which is equal to our Kronecker delta, I, J. So in our index notation, what we're doing here is we're switching the dummy variable. So the dummy variable K, we're switching its position, whether it's on the column or whether it's on the row in the operation. Either form of that gives us the Kronecker delta. Now, when we put this into coordinate-free notation, it actually becomes much clearer. This is telling us that we have A times A transpose. That's equal to A transpose A, and the product of these is simply our identity tensor. And we can actually exploit this identity here, this A transpose A, and we'll see it later on in later sections that we do use this to help simplify, particularly in the deformation problems, the operations of our equations, because we can regress back to a simple identity tensor, which is easy for us to operate with, right? So now that we got the basics of the transformation tensor, let's go and figure out how do we actually apply it to transform vectors, and then how do we also apply it and transfer tensors. So let's start with 6.1, which is the change of vector components. So how do we take a vector v and convert it from one coordinate system to another? So let's consider the vector v. V, as a representation of v with an arrow under it, is a physical coordinate-free entity, right? We haven't prescribed any base vectors or any orientation to it. We simply say it's something that exists. It's a vector, but we have no information about its orientation. But if we want to add information about it, we can. And we can actually add information irrespective to the coordinate system. meaning if we have this vector v, we can describe it in terms of an original coordinate system, so with components vi and the original base vectors ei, or we can describe it in terms of the new coordinate system, which has components vji, and we're just introducing j as just another index to show that those indexes are not the same, and ej prime, right? So by itself, the vector is coordinate free, but we can prescribe to it different coordinate systems that will lead to different values of components. We'll see that these are not equal, and we will see that these are also not equal. So both of the components vi and vi prime are components of the same vector, but they simply are described differently, right? So now let's describe the components of our new system, the new coordinate system, so the prime. And let's describe it by forming a scalar product of the vector v with the base vectors of our original coordinate system. So let's say our new vector vk, and not the vector, the components of the new system, vk prime, those components are equal to the form of the scalar, so the base vectors dot our vector v, which is, the physical quantity that has no direction, and we can then relate it back to our original base vectors. If we remember that, hey, our vector here is equal to vi ei, right? So let's go ahead and put that in there. So our base vector of the new system dot our original components vi and our original base vectors ei. Now, we know that our components here are a scalar quantity, and we know that scalars can commute out of a dot product operation. So let's pull that out, the components, and let's say that we have k dot product ei, right? So we actually have this operation here. Now, if we go back and we remember our relationships in our of A with the ek of the new base vector and the ek of our original base vectors, we can actually replace this product here, replace it with our transformation tensor. And so we actually can find, that our transformation tensor can be used and can be applied to the transformation of vectors. Now, the interesting thing is the order of these indices. Note that we have the vector here, that it's sitting before our tensor, right? So this indicates a column operation. So when we actually put this into matrix form, we'll see a very interesting configuration. Let's put it into matrix form. We'll find that we actually have columns here instead of rows. Or not columns. Well, technically columns, right? So the vector, instead of being one column, is multiple columns. So the component v1 prime, v2 prime, and v3 prime is equal to v1, v2, v3 times our transformation tensor with our normal operations here. Now, typically, we don't like to write our operations in this order. We tend to like to see our tensor before our vector to give us a new vector, right? Well, how would we do that? How would we rearrange this operation? Well, what we would have to do is we would have to reorder or switch the rows and the columns in order to make an alternative form, the form that we like to see, v1 prime, v2 prime, v3 prime. In the process of doing that, the process of reordering this, switching the indices, we'll find that our transformation tensor changes. So our diagonal remains the same, but we actually transpose the off diagonals. So 2, 1, 3, 1, 3, 2, and 1, 2, 1, 3, and 2, 3. So in order to rearrange this operation and produce the same product, we've actually ended up transposing the terms inside of this transformation tensor. So what this suggests to us actually is that the components of A are actually transposed in their original form. So in the original form, so now we finally identify the indices of the transformation tensor, right? So when we are going from our original system to our new system, the indices of that transformation tensor are Ji, Aj. So the transformation tensor in its original form actually has transposed terms. And when we reverse the process to revert back, we transpose in the opposite direction, so we switch our indices of this tensor. So that tells us that once we find our transformation tensor, if we simply transpose the terms, we can go forwards and backwards with respect to our original coordinate system and the new system that we want to define. So from the original to the new, and from the new back to the original. So now let's go into section 6.2, which is the definition of a vector. So vectors we've used a lot. Vectors are line segments that act according to the parallelogram rule, right? And the quantities represented by vectors are physical entities that cannot depend on the coordinate system used to represent them, right? Meaning that we can change our coordinate system, but the value, the vector itself, in terms of coordinate-free system, remains the same. And we know that we can then rotate from an original coordinate system into another using the equation we just found. Vi prime is equal to Aj, Vj, where Vj is in our original system, Vi prime is our new system, and A is our transformation tensor. So this definition can be used to deduce other properties of vectors. if we take or introduce our base vectors into the original rules we learned in chapter 1 for vectors, we'll find certain true properties. So for instance, say we have two vectors, I prime and vi prime. We're adding those vectors together to find a new vector that is the sum of those two, ti prime. Right? So we're adding these vectors to find the other side of the triangle from our parallelogram, right? Or the triangle rule, right? Well, what if we regress this and put it back in terms of the original coordinate system? So what if we got rid of the prime? Well, we can introduce our transformation tensors. So AJI UJ plus AJI VJ. Seeing that the J is going to disappear here, we end up with the I, right? Let's collect our transformation tensor, right? And put in brackets the UJ and the VJ. And then we can find that whenever, even though we're summing these vectors, using the triangle rule, we'll find that we can proceed with the summation operation in our original coordinate system and transform it, or we can go vice versa, meaning that we resolve this equation into simply that the sum of those two vectors is equal to the transformation of the sum of those two vectors in the original coordinate system. So we can actually use this to show that the vectors are physical quantities, and that any of the operations that we know that are coordinate free remain true, right? So now let's look at transformations in terms of tensors. So what happens if we have a tensor and we want to transform it through that coordinate system, right? It's in one system, we want to transform it to another system. All right, well, let's remember the basic relationship that we know when we're dealing with tensors. All right, so if we have some tensor f, KL, and an input tensor UL, our output tensor is VK. Remembering that from previous lectures, right? Well, we can go ahead and use the rules that we know and use our transformation tensor in order to find a form of VK. So what is VK in our new system? Well, VK in our new system will be equal to a transformation tensor. And excuse me, my pen is acting up again. There we go. Transformation tensor A MK, our tensor F in M, and our input UN. And then let's go ahead and replace the input UN such that we get A MK F. Excuse me. Let's verify these indices. We'll actually switch our indices here. Let's clean this up a little bit. So A, MK, F, M, N. So we're switching our indices. A, N, L, and U, L prime. We rearrange our indices here. In order to eliminate our dummy variables that persist. So let's see the dummy variables M, N, and L and arrive at VK prime. So if we can do so with these rearranged indices, we can then state that our VK prime if we pull out our transformation tensors as they relate to our original tensor, we can say that that is our transformed tensor f prime times our transformed input vector u. Now, because this result applies for components of all vectors of u and v, because we haven't defined the vectors u and v, we can then say that our transformed tensor fk L prime is equal to a mk f mn a n l. And let's again identify our dummy variables. Our m are dummy variables, our n's are dummy variables that are eliminated. And also, if we look at this, we can see the operations that we're performing here from row to column, and see where these dummy variables are happening. Where the first indice is row, the second indice is column. So the operation between when this one and this one is row row. So we're actually doing a row summation. On this one, we're doing column to row summations. So when we take this in matrix form, that transform matrix is the following, based on those dummy variables. Or in our first case, we're doing row row here. Operation, we'll find A11, A22, A33, and we actually have a transpose going. A21, A31, A32, A12, A13, and A23. While in our second, we actually have the proper procedure here, where the proper operation from row to column. So A11, A22, A33. And we have our normal tensor operation here. And then, of course, our f is also a normal tensor. So when we look at this, we see our transformation tensor here has these off-diagonal terms transposed. Well, the transformation tensor here does not. We can then describe this in a coordinate free form as that our transformed tensor f is equal to the transformation tensor times the tensor f times the A transposed. Remembering that A, the indices of it in their original form, right, in the form going from our original coordinate system to the new coordinate system, are transposed, right? So it may seem counterintuitive, but this represents that, and that represents that. So with this knowledge, then we can do the inverse of this operation. So the inverse would follow that our original tensor can be found in relation to our transform tensor as follows. Over AL, AJK, FLK prime, or if we rearrange it and put it in coordinate free form, the tensor F is equal to A, transform tensor F, A transposed. And so now we know how to transform a vector using our transformation tensor, as well as the equations we need to transform a tensor. And if we know this equation and this equation here, then we can use those two equations and transform tensors very easily, backwards and forwards through their coordinate system. Similarly, for our vectors, if we go back to our vector form here, we can transform vectors using these two equations from the original to the new, and vice versa. And then lastly, the important thing we need to remember, if we go all the way back, is that the components of our transformation tensor are described as cosines, which are the angles, or the angle between an original base vector and a rotated base vector. All right, so before we proceed and do an example, I want to go back and point out a typo that was in the notes. So here, when I wrote in originally was a A and an A, but it actually should be VJ here. So I've revised that. Make sure that in your notes that you also revise that typo. So let's go ahead and proceed with an example to end out this lecture. So our example for this lecture is to build the transformation tensor for a 2D rotation of a Cartesian coordinate system, right? So let's start with an original coordinate system with base vectors E1, E2, and let's draw a rotated coordinate system with base vectors E1 prime and E2 prime. So we've got E1 prime and E2 prime here. Now let's go ahead and remember that when we did the cross product of the original base vectors with the new base vectors, we found the transformation tensor Aij is equal to cosine of theta I j prime, where the j prime is related to our new coordinate system. So there are a series of angles that exist between our base vectors. So I relates to the, say the EI, and J is related to the EJ prime, right? Those base vectors. So there's actually angles that exist between the base vectors that we need to find. So let's go ahead and do that. Let's find those angles, copying this coordinate system, and piece by piece finding the angles, the cosine angles. So what is the cosine theta 1 prime? What is that angle? We're going from our E1 base vector, and we're finding the angle between it and E1 prime. That is our theta 1 prime. Theta 1 prime. And we repeat this process. Cosine theta 2 prime. The angle between base vector 2 and base vector 2 prime. Theta 2 prime. All right. What about here? cosine theta 1, 2 prime. So we go from base vector 1 to our 2 prime base vector. Base vector 1 to 2 prime. Let's draw an arrow for that one. Theta 1, 2 prime. And then our last one, which is cosine of theta 2, 1 prime. So we're starting with our base vector 2, and we're going to 1 prime, theta 2, 1 prime. Right? And it's also important for us to remember that the indice order that we found here, right? The indice order is aij cosine theta ij, and that order is actually the opposite of what we want. So this aij is actually giving us the A transpose, the transpose transformation tensor. Remember that. So we've just found A transposed here. Now, let's remember that our base vectors are orthogonal or orthonormal, meaning that there exists 90 degrees between the base vectors, right? And with that knowledge, we can actually simplify this series of 4 angles and find a single angle or a single variable that represents the rotation with respect to all of these base vectors, right? Since they're orthogonal, it's 90 degrees with respect to each base vector, each system. Let's go ahead and replace all of these thetas with a single theta that represents the rotation. So we can basically start with our base vectors 1 and 1 prime. And we can say that the angle between that is a variable theta. Since these are orthogonal, we can then say that between base vector 2 and 2 prime, we get that same angle theta, right? And then if E1 and E2 are 90 degrees with respect to each other, then we can find the angle here as 90 degrees minus theta, so the angle between E2 and E1 prime. And then there's a last angle we need to find, which is the angle from E1 to E2 prime, this full angle here, which is simply equal to 90 degrees plus theta. So 90 degrees plus theta. All right, so now that we've done that, we can then rewrite our transformation tensor. The angle between E1 and 1 prime is theta, cosine theta. The angle between E2 and 2 prime is theta, cosine theta. The angle between E1 and E2 prime, cosine 90 degrees plus theta, and the angle between E2 and E1 prime, cosine 90 degrees minus theta. So now we have this transformation tensor in terms of that angle theta. And then we can do a little bit more with it. We can replace these cosine 90 minus theta and 90 plus theta. We can replace those. And let's do that. So let's copy this and replace them. with their sign equivalents. So cosine theta, excuse me, cosine theta, cosine minus 90 degrees is sine of theta, and cosine, cosine 90 minus theta is sine theta, and cosine 90 plus theta should be negative sine of theta. Okay. So now all we have to do is, if we have the transpose, is change our order in order to get the transformation tensor. So switch our off diagonal terms. So transformation tensor is actually cosine theta sine theta, negative sine theta cosine theta. All right. So now we found our transformation tensor for rotating this 2D coordinate system, and then we can apply it by, say we have some vector v, or some vector v, and we want to transform that vector to v prime. Then so some vector v to v prime, and our v prime is simply equal to a and v, or v1 prime, v2 prime is equal to our transformation tensor cosine theta, sine theta, negative sine theta, v1, v2, right? Now we can actually derive this transformation tensor in a little bit easier of a way if we define the components of the base vectors e1 and e2 that are projected in the e1 prime and e2 prime direction. So we can actually find by saying, okay, what components of e1 and e2 are projected in e1 prime's direction? What components are projected in the e2 prime direction? We could actually find this same transformation tensor. So why not try that out? Try to find that transformation tensor through the projection method, projecting the components of the original coordinate system into the new coordinate system. So that's the lecture for today. I think I'll assign some homework at some point soon for some of these problems, particularly in this coordinate system rotation. And in our next class, we will go over principal values and principal directions. Thank you for your time and attention, and that ends our lecture for today.